Hi, this is the second part of lecture 4, that is enzyme kinetics, and we'll start with ES complex, that is enzyme substrate complex. So now, why enzyme substrate complex is important to know? Because this enzyme substrate complex is the key to understanding the kinetic behavior of a reaction. Okay, so let's see what is ES complex. So combination of an enzyme with its substrate molecule to form an ES complex is a necessary step in enzymatic catalysis. That means, I mean, suppose this reaction, enzyme and substrate is reacting and forming enzyme and product. This reaction will not just directly from this step and here to here. Okay, in between, enzyme and substrate will react and form a enzyme substrate complex. Okay, then the product will be formed. That means first the substrate will react with the enzyme and form a ES complex, and finally the product will be formed. Okay, so now at any given instant in an enzyme catalyzed reaction, the enzyme can exist in two forms. Either it will be free, okay, not bound with anyone, or it will be combined with the substrate, that is in ES form. Okay, so now at low substrate concentration, okay, I mean when the substrate concentration will be low, most of the enzyme will be in combined form with the ES. Okay, that means if substrate concentration is low, most of the substrate will be in the ES form. Okay, so in this case, the rate of the reaction will be proportional to substrate concentration. Okay, so the maximum initial rate of the catalyzed reaction, which we denote by Vmax, is observed when virtually all the enzyme is present as the ES complex. Okay, and concentration of free enzyme is very small. It's easy to understand, right? We know enzyme catalyze the reaction. To do that, first the enzyme need to react with the substrate. That means first the enzyme will form the ES form. So if all the enzyme are bound with the substrate, that means all the enzymes are in the ES form, then all the enzyme will be involved in the catalysis, right? So at that time, the maximum rate, the reaction rate will be maximum. Okay, so under these conditions, I mean, if all the enzymes are uh, bound or combined with the substrate, the enzyme is saturated in this situation, right? So the further increase in substrate concentration have no effect on the rate. I mean, say all the enzymes are, I mean, it's a saturated condition for the enzyme, and all the enzymes are bound with the substrate. So that means even if we add more substrate, there is no enzyme to bind to. Okay, so that's why in these conditions, if we even increase the substrate, more substrate in the reaction, it will be no effect on the reaction rate. Okay, and this condition exists when substrate concentration is sufficiently high that essentially all the free enzyme has been converted to the ES form. Okay, so if we wrap this assumption, then we can say it in this way. Okay, so when the substrate concentration becomes high enough to entirely convert the enzyme to the ES form, the second step of the reaction becomes rate limiting, and the overall reaction rate becomes insensitive to further increases in substrate concentration. Okay, and this idea was expanded into a general theory of enzyme action, which was idealized by two scientists, Leonard Michaelis and Muad Menton, in 1930. Okay, so now we'll talk about. Basically Michaelis and Menton, they, they derived the equation, which equation idealized this concept. Okay. So let's talk about the Michaelis-Menten equation. Okay. So what is Michaelis-Menten equation? it's a rate equation for a one substrate enzyme catalyzed reaction. I mean, by Michaelis maintained equation, we can represent the rate of a monosubstrate enzyme catalyzed reaction. Okay, so and I mean, to do that, to derive this equation, first Michaelis method, they give a basic hypothesis. Okay, so what was the hypothesis? So the rate limiting step in enzymatic reactions is the breakdown of the enzyme substrate complex to product and free enzyme. Okay, so before going to the derivative, I'll talk a little bit more about this one. So why the breakdown of ES complex becomes the rate limiting. So go back to this equation. So if you see this equation, enzyme substrate, then enzyme and product. So we can see that there are two steps in this reaction, right? This step and this step. So how we can say that this step is the rate limiting step? So the condition was the concentration of the substrate will be high. So when the substrate concentration is high enough, then what will happen? All the enzyme will be in the ES form. I mean, this step will occur readily. Okay, there will be no trouble in this step because there are enough substrate for the enzyme. So this, I mean, step will be a very easy step and will occur at once, will occur readily. So the fate of the reaction in that case will depend on this step. Okay, so the ES will form easily. So the fate of this step, that means the product, the fate of the production of the product. Okay, it will completely depend on this step. I mean, if ES form breaks down, then the product will be formed. Okay, so this is the hypothesis. Okay, so the rate limiting step in enzymatic reactions is the breakdown of the ES complex to product and free enzyme when the substrate concentration is sufficient enough. Okay, so there are some important terms if we want to give a equation for an enzymatic reaction. So, and those terms are substrate concentration, V0 initial velocity, V max maximum velocity, and a constant Km, which is called Michaelis-Menten constant. Okay, so now we'll learn how they derive the equation. Okay, so first consider this equation: enzyme plus substrate, then enzyme plus product. So, and that is actually, that every reaction can occur in forward and reverse direction. So that's why there will be like, I mean, total 4 type reaction can occur here. For this one, enzyme plus substrate, ES can then break down to EP. Okay, and the reverse reactions are also possible. So each step. So as there are 4 different reaction can occur, there will be 4 different constant. Okay, K1, K2, K minus 2, K minus 1. Okay, so now consider that the reaction is at the beginning. So that means early in the reaction. So in the early in the reaction, the concentration of the product P will be negligible because the reaction just started, so there is no product. So if the concentration of P will be negligible, this step, I mean this reverse step, that E plus formation of ES from E and P will be negligible, right? Because there is no concentration of product is very low. So if the concentration of product is very low, this reverse step will not occur here. Okay, so if we consider this condition, I mean the reaction is at the earliest step, then we can rewrite this equation in this way. Okay, E plus S, ES to EP. I mean this forward and reverse is possible, but this reverse is not possible. Okay, so now if we think about the rate of the reaction, okay, so as we are thinking about the beginning of the reaction, so here we have to denote the rate as V0. V0 means initial reaction rate, okay, or the reaction rate at the early time or 0 time. Okay, so the V0 will be determined by the breakdown of ES. Okay, and so thus the V0 becomes V0 equal to constant into substrate. We know the rate of a reaction is equal to constant into substrate concentration. So in this case, I mean, as ES is breaking down into E and P, ES will become is the substrate here. So V0 will become K2 into ES concentration. Okay. So now if we want to solve this equation, we need the value of ES concentration. However, measuring the ES concentration is not easy. So how we can do that? So we start with the total enzyme concentration, ET. So what is the total enzyme concentration? It is will be the sum of free enzyme concentration and substrate bound enzyme concentration. So that means free enzyme will be total enzyme minus ES, right? ES is the substrate bound enzyme. So okay. Now, if the substrate concentration is much higher than the total enzyme concentration, okay, so what will happen? So that the amount of substrate bound by the enzyme at any given time is negligible compared with the total substrate concentration, right? Because if the substrate concentration is very high, the total is very high, okay, in that case the concentration of total enzyme will be almost negligible if we compare with the substrate concentration. Okay. Okay. So now, if we think about the breakdown of the ES, okay. So what happens in this reaction? ES is formed and then the ES breaks into the product. Okay. So the rates of formation and breakdown of how we can determine this one. I mean, how we can determine the rates of formation and breakdown. Okay. So these are determined by the constant and also by the substrate concentration. So if we think about the rate of ES formation, it will be K1 into this. Why? Because the rate of the ES formation will be this step, right? When the ES is formed in this step. So the rate of this step will be this constant into enzyme concentration into substrate concentration, right? Okay, so K1 is the constant, then substrate concentration and enzyme concentration, and we just saw which enzyme this one, the free enzyme, and we just saw from here that free enzyme equal to E2 minus ES. So the rate of formation becomes like this. Okay, so now what is the rate of ES breakdown? So if you want the rate of ES breakdown, we have to see in which step ES breakdown. Actually, in this reaction, there are two steps, okay, where ES can break down. First, this step, ES can break down into enzyme and product, or ES can break down into enzyme plus the original substrate. I mean, this forward step and reverse step. So if you want to consider the determine the calculate the rate of the ES breakdown, we have to consider both these steps. So in that case, the rate of the ES breakdown will be sum of rate of this step and rate of this step. Okay, so thus it becomes like this one. Rate of ES breakdown equal to K1 into ES plus K2 into ES. Okay, constant into ES, this constant into ES. So now, what happened in the equilibrium? Okay, so some important assumption about this reaction. So what the important assumption? The initial rate of reaction reflects a steady state in which ES is constant. So that is, the rate of formation of ES is equal to the rate of its breakdown, and this is called a steady state assumption. I mean, this is almost like the equilibrium. What happened in the steady state? The forward reaction rate and the reverse reaction rate will be same. Okay, or we can say that the amount of ES formation and the amount of ES breakdown will be same. So if it is true, I mean, if so, that means in the steady state formation, steady state, these two rate will be same. So we can write it in this way. Okay, the rate of ES formation will be equal to rate of ES breakdown. Then if we simplify this equation, it will become like this: E1 ET ES minus K1 ES S equal to ES K minus 1 plus K plus 2. Okay, I will suggest you to just derive it okay, in your notebook. So if you just practice it, I mean, it's not that stuff, right? It's just solving an equation that we have done. I mean, you have done several times, okay, when you are doing math. So it's simply like that, okay. So then we'll add the K1 ESS to both sides of the equation, and then the simplifying will give this form. And if we take ES in the left hand side, then in the right hand side it will be like this. And then if we further simplify it, the expression will look like this: ES equal to ETS divided S plus K1, K minus 1, K plus 2 divided by K1. So we can see here all these denominators are constant. So K minus 1, K2, K1, all these are constant. So if we can substitute all, I mean, as all these constant are in a, I mean, in a same place, so we can substitute this with another constant. That constant is the Km. Okay, and Km is called the Michaelis-Menten constant. Okay, so if we replace this with the Km, then the equation become this: Es equal to ETS divided Km plus S. Now, at the beginning, we saw that V0 equal to K2 ES. So if we put the value of ES that we got from here into this equation, then V0 becomes K2 ETS divided Km S. Okay. So now, if we think about the maximum velocity. So when the maximum velocity occurs, when the enzyme is saturated, okay, that means when an enzyme is saturated, the concentration of ES is equal to ET, which we already discussed why here, right? So that means the maximum velocity Vmax occurs when the enzyme is saturated. Okay, then the Vmax can be defined as K2 ET, and the equation becomes K as K2 ET equal to Vmax. The equation becomes V0 equal to Vmax into substrate concentration divided by Km, Michaelis-Menten constant, plus substrate concentration. Okay, so this is the Michaelis-Menten equation. Okay, and it's the rate equation for a one substrate enzyme catalyzed reaction. Okay, so it is a statement, and this equation is a statement of the quantitative relationship between the initial velocity V0, the maximum velocity Vmax, and the initial substrate concentration, and all related through the Michaelis constant K. Okay, so now from this Michaelis uh, maintained equation, we can uh, do a, and I mean, we can derive further. So in what way? This way. So an important numerical relationship emerges from the Michaelis-Menten equation in the special case when V0 is exactly one half of the Vmax. Okay, so this is very useful practical definition of Km. Okay, this is very useful actually. Then what is the practical definition of Km? It is Km is equivalent to the substrate concentration at which V0 is one half Vmax. Okay, this is the definition of Km. So if we consider that V0 is exactly half of the V maximum, then we can substitute the value of V0 by Vmax by 2, half of the Vmax. V0, as V0 is half of the Vmax. So then Vmax by 2 will be Vmax substrate concentration divided Km plus substrate concentration. We can omit Vmax from both sides, and eventually the equation becomes this: Km equal to substrate concentration. So, I mean, from this equation, we can give a definition of the Km, that what is Km. So, this is Km. Okay, so when V0 is half of the Vmax, Km is equivalent to the substrate concentration. Okay. Okay. So, now we can graphically, if we graphically represent the Michaelis-Menten equation, how it looks like. So, in graph, we want to plot the Michaelis-Menten equation. So to do that, in x-axis, if we put the value of substrate concentration in millimolar, and in y-axis the rate V0. Okay, its unit is micromolar divided minute. Okay, micromolar per minute. So the equation becomes like this. Okay, so what we understand from this equation is written here. Okay, so the Michaelis-Menten equation dependence, that means dependence of initial velocity of substrate concentration. So what we understand from this graph shows the kinetic parameters that define the limits of the curve at high and low substrate concentration. So at so now when the substrate concentration is low, that means Km much greater than substrate concentration, and the substrate concentration term in the denominator of the Michaelis-Menten equation becomes insignificant. That means when the substrate concentration is low, okay, the the substrate concentration term becomes insignificant. Okay, so in that case, we can simplify the equation as this: V0 equal to V max substrate concentration divided Km. Now, okay, so in this case, if we simplify the equation or replace this equation in this way, we can say that V0 exhibits a linear dependence on the substrate. Okay, from this equation, we know that V0 depend on these three parameters, right? Vmax, S, and Km. Here, the only variable is substrate concentration. That means we can say that V0 has a linear dependence on the substrate concentration. Okay, so if the substrate concentration increase, V0 will increase. If the substrate concentration decrease, V0 will decrease. Okay, so now this was when the substrate concentration was low. Now what will happen when the substrate concentration is high? Okay, so that means substrate concentration is much greater than the Km. Okay, so in this case, the Km term in the denominator of the Michaelis-Menten equation becomes insignificant, and then the equation becomes this: V0 equal to Vmax. Okay, so from this equation we can see that this is consistent with the plateau observed at high substrate concentration. Okay, so the Michaelis-Menten equation is therefore consistent with the observed dependence of V0 on substrate concentration, and the shape of the curve is defined by the term Vmax by Km at low substrate concentration and Vmax at high substrate concentration. Okay. Okay, so that's all for this part. In next part, we'll talk about Lion-Weaver part equation. So, thank you. See you in the next lecture.